Module 4, Voltage and Current Division. In this module, we'll examine some important properties of resistive circuits. A resistive circuit is one that contains only voltage sources, current sources, and resistors. We're familiar with the voltage source and the resistor from previous modules. The current source is a new circuit element that we'll talk about in a moment. Let's talk about the current source. A current source is a circuit element that forces a constant current to flow out of its positive terminal. A current source is not a naturally occurring element like a voltage source, in that it must be synthesized from other electronic components. It's also useful for modeling the behavior of certain electronic devices. We note that current is defined as positive when flowing out of the positive terminal of the source. Hence, the source is active and it provides power to the rest of the circuit. In contrast to a voltage source, for which the voltage is constant and the current is determined by the rest of the circuit, the current out of a current source is constant, but the voltage across it is determined by the rest of the circuit. Now let's get back to resistive circuits. They're found everywhere, wherever there's electricity. We've already seen one example, the simple flashlight. Here's the physical circuit. Two 1.5 volt flashlight batteries connected in series for a total voltage of 3 volts, connected to a half-watt light bulb. We can represent this physical circuit by the following equivalent circuit model: a 3-volt voltage source and a resistance of value 18 ohms. Here's how we determine that the resistance has a value of 18 ohms. We know that the bulb consumes a half-watt of power, and that power is equal to the product of the voltage across the bulb times the current through it. So we can find the current by dividing P by V, as we've done in the equation shown below. The result is 167 milliamperes. The equivalent resistance of the bulb is then computed by the ratio of V to I, 3 volts divided by 167 milliamperes, or 18 ohms. Here's another example that comes from everyday life. It consists of an automobile storage battery and the starter motor that first turns the engine when we turn on the car. Let's suppose we know that the starter motor appears like a resistance of 0.1 ohms to the voltage source. That's a reasonable number for the average car. We can use this simple model to determine the current flowing into the starter motor. I is equal to V over R, or 12 volts over 0.1 ohms yields 120 amperes. That's a lot of current. Now let's talk about how we solve for the voltage and current values in a more complicated resistive circuit. Here's an example. Our objective is to find the currents I1, I2, and I3. To meet this objective, we'll use the same tools that are used to solve just about every resistive circuit. Kirchhoff's voltage law, Kirchhoff's current law, and Ohm's law. It's very appropriate that we use Ohm's law to solve a resistive circuit because it describes the relationship between voltage and current in a resistor. Let's first apply Kirchhoff's voltage law and Kirchhoff's current law to the circuit. One statement of KVL is that the voltage between two nodes is independent of the path taken. We can apply this concept to the voltage between the two nodes labeled in green. If we evaluate the voltage over the blue path, we arrive at V1. If we evaluate the voltage between these nodes over the red path, we get the result V0. Hence, it must be true that V1 equals V0. And we know V0 from the statement of the problem. It's 12 volts. We can also evaluate the voltage between the green nodes over the orange path. And that voltage is equal to V2 plus V3. Hence, the sum of those two voltages must also equal V0, or 12 volts. Now let's apply KCL to the blue node. KCL states that whatever flows into a node must flow out. Hence, the current I2 must equal I3. The information we've obtained so far is shown in the blue box in the upper left-hand corner of the screen. Let's next apply Ohm's law to the circuit. Remember that our objective in this problem is to find the currents I1, I2, and I3. For resistor R1, we know that I1 is equal to V1 over R1. Similarly, we know that I2 is equal to V2 over R2, and I3 is equal to V3 over R3. The information we've obtained so far is summarized in the blue box. We're ready to solve for the desired currents. We have everything we need. We can solve for I1 by simple and direct math. I1 is equal to V1 over R1, or 12 volts divided by 4 kiloohms, which equals 3 milliamps. Finding I2 and I3 requires a bit more math. We express the voltages V2 and V3 via Ohm's law as I2R2 and I3R3. And then we use the information that I2 is equal to I3 to obtain the equation shown. We can now solve for I2 in terms of V0, R2, and R3. I2 is equal to V0 divided by the sum of R2 and R3. If we substitute in the numbers, we get the result 4 milliamperes. Note that we could have found this result in another way by simply viewing R2 and R3 as a series combination of resistors equal to 3 kiloohms. We know that the voltage across this equivalent resistance is 12 volts. We'd arrive at the same value for I2. Finally, we use our knowledge of KCL to find the value of I3, which has to be the same as I2, 4 milliamps. We're done with the problem. We've met our objective. Let's use these answers to find out some other things about the circuit. Here's one question. How much current flows out of the voltage source V0 as I0? We can find the answer by using Kirchhoff's current law at the node labeled in green. I0 is equal to I1 plus I2. If we plug in the values we found for I1 and I2, we get the answer, 7 milliamps. Here's another question. How much power is delivered to the circuit by the V0 supply? We find the answer by multiplying the voltage V0 times the current I0. The answer is 84 milliwatts, or 0.084 watt. We're now going to talk about voltage division. It's a property of resistive circuits. Let's take a look at the simple resistive circuit shown below. One voltage source, two resistors in series. It's a topology that's found in many applications. We'd like to solve for the voltages V1 and V2. If you don't remember what topology means, it's the basic wiring map of the circuit, independent of the components. Here's how we solve the circuit to find the voltages V1 and V2. We know from Kirchhoff's current law at the green node that I1 is equal to I2. We also know from Kirchhoff's voltage law around the one loop in the circuit that the sum of V1 plus V2 is equal to V0. And from Ohm's law applied to each resistor, we know that V1 is equal to I1 R1 and V2 is equal to I2 R2. We've obtained all the relevant information from the circuit, so we should be able to solve for the desired variables. First, we take KVL and write the voltages in terms of their current resistor products as given by Ohm's law. We next make use of the KVL expression to express I2 in terms of I1. We solve for I1. It's equal to V0 divided by R1 plus R2. With a little practice, you should be able to arrive at this result by inspection, because the two resistors added together form an equivalent resistance, R1 plus R2, and it's connected across a single voltage source. So you only have to apply Ohm's law to the equivalent resistance as a whole. We can now solve for the desired voltage V1 as follows. We know that I1 is equal to V0 over R1 plus R2. So we get V1 by multiplying I1 times R1. Remember, because of Ohm's law, if you know the voltage across a resistor, you know the current through it, and vice versa. The result is the formula in the red box. V1 is equal to the total voltage V0 times R1 over the sum of the resistors. We call this formula voltage division. It's helpful to remember the voltage division formula in words. You take the voltage that is being divided, and the voltage that you want to compute is equal to the total voltage times the resistor across which you want it, divided by the sum of the resistors. Or, for short, the resistor you want divided by the sum. We can do the same thing to solve for the voltage V2. We again know that I1 is V0 divided by R1 plus R2. In this case, I2 is the same as I1. So to get V2, we simply have to multiply its resistance R2 by I1, as shown in this equation. Here's the voltage division formula again, this time applied to R2 and the voltage V2. The circuit diagram and formulas shown below summarize the voltage division principle. It might be a good idea to print out this slide and keep it in a notebook for reference. It's also well covered in the textbook. Here's how we apply voltage division when we have more than two resistors. The principle is the same. The formulas shown to the right of each resistor summarize voltage division succinctly. The voltage across the desired resistor is equal to the total voltage times the one you want divided by the sum of all the resistors. The formula we derived applies only if no connection is made to the terminal between the resistors. A more accurate way of stating the restriction is that no current can be drawn from the terminal connecting the two resistors. The reason for this restriction is, as you recall, that solving the voltage division equation required that I1 be equal to I2 for the junction between resistors R1 and R2. If current is drawn off through a third branch connected to the node, then this statement of KCL will no longer be true. A bit of caution is in order with respect to voltage division. Here's a circuit where voltage division works when applied to the resistors R2 and R3. Nothing is connected to the node that joins these two resistors. The voltage applied to the series combination of R2 and R3 is V0, so we can use voltage division to get V3. The result is that V3 is equal to V0 times R3, the resistor we want, over R3 plus R2, the sum of the two resistors. If we plug in the numbers shown in the circuit, 12 volts, 1 kilo ohm, and 2 kilo ohms, we get the result, 8 volts. You may recall that we analyzed this circuit earlier in the module, using direct calculation by KVL, KCL, and Ohm's law. We previously calculated that I3 was 4 milliamps. Let's see if our answer is consistent. According to Ohm's law, V3 should be equal to I3R3. That's 4 milliamps times 2 kilo ohms, or 8 volts. Our answers are indeed consistent, so we're happy. Now let's look at an example where voltage division doesn't work. We might be tempted to apply voltage division to the resistors R1 and R2 in this circuit. After all, VA is connected across what appears to be their series combination. If we apply the voltage division formula, we get the following result. V2 is equal to VA times the resistor R2 over the sum of R1 and R2. If we plug in the numbers, we get the answer shown, 7.2 volts. But the caution comes to mind here. Something is connected to the junction between R1 and R2. This answer is just plain wrong. Let's try and find out what went wrong. Let's solve for V2 directly in this circuit using KVL, KCL, and Ohm's law. There's a bit of algebra involved, so let's get going. The first step is to take KVL around the left-hand loop. We'll call this equation 1 for reference purposes. V2 is equal to VA minus V1. We've arranged the terms a little bit algebraically, but I'm sure you can follow. And in another step in the same equation, we just apply Ohm's law for V1, expressing it as I1 R1. From KVL around the right-hand loop, we get equation 2. V2 is equal to VB plus V3. And we again express V3 in terms of its I3 R3 product. And finally, we apply KCL at the node labeled in blue. I1 is equal to I2 plus I3. Our objective here is to find the current I2. Remember that if we know the current I2, we can find V2 via Ohm's law for the resistor R2. Now we do some more algebra. Equation 1 transforms as follows. I1 is equal to VA minus V2 over R1. Equation 2 can be similarly transformed to yield I3 is equal to V2 minus VB over R3. We've now got independent expressions for I1 and I3, which is what we need to find I2 from the KVL equation 3. Here's equation 3 again. We can express it in the following way. I2 is equal to I1 minus I3. We now substitute in the expressions for I1 and I3 found from equations 1 and 2. We get the following expression for I2. VA minus V2 over R1 minus V2 minus VB over R3. Remember, our goal is to find an expression for the voltage V2. So the next thing we want to do is express I2 as a voltage V2 over R2. We move all the terms involving V2 over to the left-hand side of the equation. Here's what we get. Finally, we solve everything for V2 and get the complicated expression to the right. Note that it contains components of VA and VB, plus all the resistors in the circuit. This answer is certainly not the same as the simple voltage division expression that we were tempted to use in the beginning. We're now in a position to look at the analog to voltage division, and that's the property of current division. Again, it's a property of resistive circuits. Let's consider the simple circuit shown below: a current source and two resistors R1 and R2 in parallel. This basic topology is also found in many applications. As mentioned previously, the current source is not a naturally occurring source, but it can model the current I0 produced by some other circuit or another part of the circuit. We know from Kirchhoff's current law that I0 will split into I1 plus I2. But we'd like to know the ratio of I1 to I2. Here's how we solve for I1 and I2. From Kirchhoff's voltage law between the upper node and the lower node, we know that V1 is equal to V2. We can express these voltages via Ohm's law for each resistor. We thus convert each voltage value from KVL into a current value. Combining these KVL and Ohm's law expressions leads us to the result that I2R2 is equal to I1R1. We next write down Kirchhoff's current law for the upper node of the circuit. I1 plus I2 is equal to I0. We can manipulate this formula algebraically to express it as I1 is equal to I0 minus I2. We can then express I2 as being equal to I1 times the ratio of R1 over R2. We arrive at this result by dividing the above equation by R2 on both sides. We can then substitute the expression we derive for I2 to arrive at an equation that has only known quantities plus a single variable, I1. We can solve this last equation for I1 to arrive at the formula shown to the right of the green arrow. This form of the equation for I1 is not the most convenient, so let's transform it a little bit. Let's take the formula for I1 from the previous slide and manipulate it in the following way. Let's just multiply the numerator and the denominator by R2. What we get is the expression in the yellow box. The current I1 is equal to I0 times the ratio of R2 to the sum of R1 plus R2. We call this equation the current division formula. It has a form similar to the voltage division formula, but it differs in one important respect. When we use the current division formula to compute current through one resistor of a parallel pair, the numerator in the expression is the resistor that we don't want, and it's divided by the sum of the two resistors. In a manner that parallels what we did for voltage division, we can extend this result to accommodate more than two resistors in parallel. If you examine the three expressions for I1, I2, and I3, you'll find that they follow the same pattern. To find the current you want, take the total current flowing into all the resistors, multiply by the resistor you don't want, divided by the sum of the resistors. In this case, the resistor you don't want is the parallel combination of all the other resistors. Let's summarize what we've learned in this module. Resistive circuits contain voltage sources, current sources, and resistors. Resistive circuits can be solved using Kirchhoff's voltage law, Kirchhoff's current law, and Ohm's law. Voltage division allows us to solve for the voltages across resistors in series. Current division allows us to solve for the currents flowing through resistors connected in parallel.